So, good evening, ladies and gentlemen, and you're very welcome to this evening's lecture. My name is Ronan Keane. I'm the Chair of Engineers Ireland Cork Region, and I'd like to welcome you to tonight's lecture on the installation of large monopiles as offshore wind foundations using impact hammers or drills. So I'm delighted to have our speakers this evening, who are Fabian Hippe and Ivan Hartnett. Fabian is the Managing Director of Mink GmbH, a global leader in the manufacturing operation of offshore piling hammers. Fabian is a geotechnical engineer by training and has led Mink in its development of the new generation of impact hammer required for 8-meter plus monopiles. Ivan then is the Renewable Business Development at Acton, which is Mink's parent company. Ivan has worked with Acton and its group companies Mink large diameter drilling and coring grout services to develop the drilling and grouting equipment required for the installation of large monopiles in challenging ground conditions. So without further ado, I'll hand you over to Ivan, who's going to start the lecture.
Good evening. Thanks very much for the time, Ronan, and for the chance to speak to you guys. I don't think a lot of people were expecting to be doing a presentation like this the day before St. Patrick's Day, but that's just the strange times we live in. What I'm going to start off with is just an introduction to the businesses that we're going to talk about today. So Acton is the parent company, and then we're going to talk about 3 of the daughter companies of that parent company. Then a market overview of how the wind farm market is developing, particularly large monopiles or extra large monopiles. Then Fabian will take over and talk about piling hammers, the developments within piling hammers. Then we'll talk about pile drills for the installation of monopiles, pile grouting, and the future of where we see things going. Okay. So, as I said, I work for Acton. Acton is a UK-based business that has several businesses, offshore and subsea engineering businesses that focus on back-of-the-boat services in oil and gas and in renewables. In the renewables market, we provide services across the life cycle of the wind farm project, from site investigation through our survey businesses, through the engineering and design of the foundation concepts, and then coming on to the installation, where we provide pile installation equipment and survey support on vessels, which is the area that we'll talk most about today. And then when it comes to the operation side, we provide asset integrity and structural monitoring through our monitoring businesses. And then a topic that's potentially coming more to the fore over the next 3 or 4 years is decommissioning of wind farms. At the moment, though, there's no real opportunity for decommissioning of wind farms in the Irish market, but it's something that is starting to occur in the UK and in the European markets. So the 3 areas that I'm going to talk about, or that we're going to talk about today, are simple concepts, and are concepts that people probably come across in normal life. So it's hammering, as in using hammers to drive something into a surface. It's drills, using a drill to install something, and then grouting, which is filling cracks with a material. The only issue is that we do it at a larger scale. So first of all, our hammer business is Mink. Mink are based in Galkenkirchen in Germany. Then our drilling business is large diameter drilling, which are based in Falmouth in Cornwall in the UK. And then our grouting business, Core Grouting Services, is based in Cork. Core have an office in Bishopstown in Cork, and then a yard in Crookstown as well, where we store our equipment and test our equipment before it goes offshore. So Mink is by far the oldest company within our group, established in 1868 with about 145 employees, based in Galkenkirchen in Germany, as I said. Mink have a long track record of installing monopiles, or installing offshore structures, and installing in both oil and gas and in wind. So since about 2000, Mink has been driving piles for offshore wind structures. in some of the most recent projects, like Triton was a big monopile project, Amram Bank, then another German offshore project, and Rampion was a big UK project for monopile installation. LDD was established in 2007 in Falmouth in Cornwall. Cornwall, drawing a lot of the heritage in Cornwall from mining and drilling down there. So there's a lot of expertise there when it comes to offshore and nearshore operations and drilling. LDD have about 55 employees and are currently working on several wind farms in China for large diameter drilling of monopiles, and then have good UK experience as well, Grouting and Burbo Bank. Core Grouting, as I said, is based in Cork. We set it up in 2013. Currently, there's about 30 employees, and Core are going through a big growth phase at the moment. And they've done several wind farms as well, European-based wind farms, and are now moving into the Taiwanese market from a wind farm installation point of view. So when we look at the wind, sorry, let's go back a second. So when you look at the wind market, there's about 32 gigawatts of installed capacity of wind farms in 2020. And that is expected to grow dramatically over the next 10 years. Originally, the growth to come from China, which is quite a difficult market. We've sold a lot of equipment to China, but the Chinese want to do all their own services themselves. Whereas the other Asian markets and European and North American markets is more of a service-driven market. We see significant growth between now and 2024, and then an even bigger growth 2025 onwards, when you've got the US and the Japanese market and some of the other Asian markets really pushing hard. And then you've got some new European markets coming in. Poland has made a big commitment to wind. France has made a big commitment to wind and started developing the projects. And then Ireland is also another area that's made a big commitment to wind, and we're looking at maybe up to 5 gigawatts of offshore wind power in Ireland. And looking at the ground conditions from the early stages, it looks like there will be relatively challenging ground conditions, and there will be using as big a monopile or as big a turbine as it can, which probably leads itself to big monopiles, a big monopile installation equipment. So one of the other trends with the wind farms is not only that there is going to be a lot more of them, it's also that the wind farms on average are getting bigger in size, as in the amount of power generated by each individual wind farm is going to be bigger. And with the need to drive down the cost of energy, developers want to use the biggest turbine that they can on the most cost-effective foundation. So currently we're looking at an average of like 6.5 is the current average across the wind farm for the size of the turbine across the wind farms. That average is going to like 10, 12, 2025, and we see 15 megawatt turbines coming on stream, which is leading to larger diameter, longer, heavier monopiles. So these monopiles shown are the Yunlin monopiles. They're looking at up to a weight of 2,500 tons for the monopiles, bottom diameter of 11 meters, tapering down to a top diameter of about 8 meters. So these are extremely big foundations. And it looks like these will be used a lot more on future wind farms due to the need to decrease the cost of energy and support larger turbines on top of these monopiles. So I'll hand over to Fabian to talk about how we see the hammers, how these will interact with these large monopiles. Okay, Fabian?
Certainly, and thank you very much, Ivan, and thanks, Ron, again for the warm welcome to this webinar. As stated, Mink is long-standing business in the renewable industry, as well as in the pile driving business. Established in 1868, we have developed pile driving hammers from day one through the periods today, and we are one of two primary suppliers for the renewable business, but oil and gas business as well, where we do supply hammers of variable sizes, starting with 100 kilojoule small hammer sizes that you see on the bottom left graph on the very left side here. all the way up to 4,400 kilojoule hammers. To put this in perspective, a 3,500 kilojoule hammer compares to a Porsche 911 driving at 200 kilometers per hour and crashing against the wall. And that's the energy that the hammer actually puts out on a blow-by-blow basis. With these hammers, we can drive piles in the range of 0.5 meter, with the smallest one certainly up to 315 inches or 8 meter diameter on the top. And we can take some of the hammers down to 3,000 meter water depth. And this is certainly not applicable for renewable energy per se, but for oil and gas assets where we do install mooring anchors for floating foundations. Or the renewable business, and that's certainly the primary point of discussion for this talk here. We're focusing on the large energy hammer range. There's a family of hammers that we've put into the market starting in 2015, where we issued the first hammer of its size, a MHU 3500S that you see in the center page. From that hammer, we diversified out to a smaller size hammer, 2400S, as well as a larger hammer, 4400S. All of these hammers are today in the market and are part of one family. One family means that we have synergies between these two individual systems. For example, the hammer housing is the same diameter, the drive unit is similar and comparable to one another, and adaptations can be readily exchanged between these. Though notably, the energy spread that we do see with these hammers is quite significant, ranging from 2,400 kilojoules all the way up to 4,400 kilojoules maximum. Looking at this family in terms of its versatility and what we can do with this, you'll see on the graph on the right different configurations for different applications. In renewable industry, we predominantly drive monopiles and lead therefore a large adaptation of variable sizes, 5 meter plus, to adapt to the monopile directly, either directly on top of a pile or on top of flange. We talk about flanges in a minute. But other renewable assets are being developed using jacket foundations. So it's a multi-pile foundation system similar to what is known from oil and gas, a steel structure erected then on top of that, and the foundation pile is a driven pile for that purpose. Consisting of 3 or 4 piles per wind turbine generator. And for that, we use a smaller diameter, and you see that resembled on the 2 left graphs. The red boxes behind each of these hammers marks an additional unit. With the renewable energy push that we've seen developing over the years, there's a strong push, of course, into the environmental and environmental friendlier system technologies into the market. That does not only relate to how much exhaust do we put out with our diesel engines that run our hammers, diesel hydraulic power packs that we use, but it also relates to the environmental footprint that we leave in the water column, for example, by means of piling noise, and we come to that. The unit that is marked by red is a MNRU, it's a Mink noise reduction system underwater. And it reduces the piling noise underwater that is actually advantageous for mammals in the area when we pile drive. With the family, we see a lot of benefits coming in terms of the R&M opportunities that we have. We can readily exchange spare parts and therefore reduce our spare parts cost quite significantly. But we can, of course, exchange adaptations equally as well. So I can use any of the adaptations that you see on the graph with any other hammer as well, and it's versatile in terms of exchangeability. Same applies for the MNRU. So each hammer that you see with the MNRU in the red box is actually one and the same unit and can be swapped over from one to the other. And that provides, of course, cost savings on our end that we can pass on to the market to make it more economical to install foundations. Notably, those systems are heavy. So for the largest hammer, the 4400S with an 8 meter adaptation, we're talking about 774 tons in weight. That is, of course, high grade steel, and those are notably high cost that we have to invest in order to provide these systems into the market. Let's take a minute for the adaptation and what is the adaptation. The adaptation is the component that actually touches the piling good, so the pile itself. So each of the anvils that you see on the bottom line sits directly straight on top of a steel pile that you saw on the picture earlier. All these anvils have definite diameters, and the nominal diameter that you see is the range that we can drive piles with for the nominal diameter, but it is a solid steel piece, fully forged out of one component, one pouring, one ingot, and therefore quite heavy in weight. For example, the one on the bottom right over here, that's a weight of approximately 250 tons. The center piece for a 7.5 meters, about 228 tons, while the one on the left is about 90 tons. So they're quite nominal, quite heavy, and therefore difficult to come by. And we are comparing that technology to what we can actually tap on the market. In the global market, there may be 4 to 5 forging companies in the world that can provide us with this kind of plate. And therefore, it's a very limited market. And we're talking about technology that is hard to procure and difficult to design and obtain. Piling hammers per se have been built and provided into the market to install piles for foundation purposes. The driven pile is one of the oldest but also most reliable foundation systems that is available in the market in the civil engineering arena today. Though it provides us challenges when we of course now go into the environmental aspects for many reasons. Piling noise, be it in civil construction near civilization, urban areas, or even offshore as well, provides an adverse impact to the environment or people per se. That's of course no difference than when we move offshore. For that reason, we are looking into improving that and reducing our piling noise footprint in that area. In Germany, there has been regulatory bodies have set forth a maximum limit of piling noise at 160 dB. This is measured underwater, 750 meters from the piling good, from the pile itself in a distance. And notably, as you can read from the graph, the black dots do show the peak level of our piling noise at 750 meters, and we need to mitigate this down to 160 or 190, depending on what level we are looking at. Now, that's quite significant contributions that we need to make, notably that 6 dB means 50% loss of energy in the noise. For that, we have redesigned our hammers in various aspects, but we are not only depending on primary noise mitigation aids, meaning by structural design, we are also depending on secondary aids in order to overcome this challenge. The reduction of 20 dB means about 90% of energy is absorbed by that reduction. And that's quite significant in terms of the protection of the environment. Secondary noise protection systems like underwater bubble curtains or mechanical aided systems are required in order to actually overcome this. Most of the installations that we do today are dependent on 2 to 3 secondary noise mitigation systems. Therefore, we've taken an initiative at Mink to reduce the primary source of the noise, which is the hammer itself, and make it more friendlier to the noise stimulation that we put on top of the pile. And we designed this M&R unit, and I'll show you parts of that in a minute. The M&R unit is a modular piece that can be mounted between the hammer housing and the anvil itself. The white piece on the bottom here on both of these hammers, and I hope you can see my cursor, is the pile sleeve with the anvil in it. You see a cross-section cut on the right side or on the center picture here. And there's an individual piece mounted in between the ram weight that strikes on top of the M&RU blocks and then extracts the energy down into the anvil. Firstly, what we do with this, we actually we stimulate the pile in the same manner, but we actually change the force time characteristics of the blow that we put on top of the anvil. And that allows us to actively reduce noise by 3 dB while we do maintain the drivability. 3 dB does not sound massive if you consider that you have 199 or 200 dBs noise. However, it is a massive contribution to the overall task that we have on our hand, and any dB actually counts on that. While noise mitigation is on the forefront, there are lots of other features that make large piling or pile driving of large diameter piles more challenging. Normally, we have access to the hammer at all times, and we can actually maintain it in a horizontal position. So we can lay it down horizontally on deck and can access any part of the hammer. With a large adaptation, this becomes a little bit more challenging. Due to the physical size of the system stands upright on board the installation vessel. Therefore, we cannot reach every single piece of the hammer easily. We either need large scaffoldings to do so, or we need to do smarter and design smarter systems to actually make it accessible. The common design of the MHU hammer, for example, incorporates a shock absorber. The shock absorber you can compare to a shock absorber on your car. Actually, it avoids and reduces the wear and tear on the surrounding structure that is put onto the system purely due to the usability of it. So any strike, any energy that we put into the pile, of course, is reflected by the pile and is being pushed back into the system. We try to protect with this shock absorber, we try to protect the critical components of the hammer, like the drive unit, from this returning shock wave. The shock absorber commonly was built in the older systems into the hammer foot and was not accessible from the outside. In order to maintain this shock absorber, we had to dismount the pile sleeve on the bottom, take out the anvil, and then can take out the shock absorber. When we store the hammer now, the offshore wind hammer in a vertical position, this is a little bit more difficult to access. And even if you imagine you have a 250-ton anvil sitting on top of it, that's quite a heavy lift to overcome in order to get access to that. For that purpose, we have redesigned the entire shock absorber and made it accessible to the outside. Rather than having one solid ring with individual shock absorber cartridges, we designed a ring with individual shock absorber cartridges, which can be man-lifted out of the hole and exchanged easily. Each of these cartridges is continuously monitored, as we need to maintain a pressure of 300 psi in the cartridges to provide the continuous shock absorber competence of the system. Just that little feature allowed us to increase the availability of the system offshore and reduce maintenance quite significantly. Other system technologies that we developed to overcome challenges are protective systems in order to protect the pile itself. In oil and gas assets, most piles are being driven as a bare steel pile. There's hardly any coating on these piles to protect these from ambient water and therefore from corrosion. That is mostly due to the fact that these piles are either grouted after they have been driven and therefore protected by the grout, or they are actually penetrated into the soil. In offshore wind, it's a little bit different. We have a pile that is penetrated into the soil, extends through the water column, and then through the splash zone above water. You have, of course, the soil protected area, but you equally have the corrosive environment above surface and in the splash zone that needs to be protected. For that purpose, the piles are coated or painted to protect it from this corrosion. This corrosion coating or paint, again, needs to be protected from the Mink hammer, and therefore we require special strip systems in order to protect it from scratches. The pile sleeve, of course, is made out of steel, and we have designed and developed within the university a composite material that is actually mounted on top of these steel strips to protect then the pile that is sitting in the center of this pile sleeve. This pile sleeve is the real thing and is the component that we look at on the right picture on the bottom here. Well, piling seems to be quite easy, and the introductory slide that Ivan showed with the sledgehammer, let me call it, suggested the mechanics behind it are quite straightforward. However, we needed to make piling a little bit smarter. There's quite extensive control mechanisms involved in order to get the best out of the system and certainly protect the system from its own forces, as well as ensure that we are protecting all goods at the same time and install the system to the grade that we anticipate. That may be by means of verticality as well as by elevation. To ensure verticality or horizontality, as a matter of fact, of the flange, we have designed a Mink horizontality measurement system. The system is readily built into the hammer and sits on those little buckets that you see in silver on the hammer foot, and allows us to ensure that the horizontality of the pile top within plus minus 0.1 degree. That's quite significant and a very strong contribution to the installation effort, and makes actually quite a bit of survey redundant at this time. We continuously see the position through a bullseye, a digital bullseye in our control system, and the blue screen that you see on the right is a screenshot from the control system that the operator sees during piling. With that, we can certainly monitor and observe how this verticality changes over time. The operational setup for a 3500 hammer, or the 24-4400 equally as well, is quite comparable between the hammer families. It requires massive hydraulic volume flow in order to make it, put it in operational modes and move the ram weight strike it on top of the anvil. The 3500 runs best at approximately 4,800 liter hydraulic fluid. This is per minute. So for that, we require three large power packs, 1,600 liter each. Each measures 40-foot high cube that takes on a deck spread that measures about 15 by 15 meters. That's quite significant in just the physical assets that we need to put out. The hydraulic fluid is run through 8 hoses, 4 for high pressure to feed the hammer and 4 to return the fluid, 2.5 inches in diameter each, and bring quite a bit of weight with them on its own. Through this, we can, of course, move the ram and deliver the energy that we want. The acceleration that we cause with this is quite significant as well. We are seeing accelerations that, of course, put load onto the physical system as well. But even if we store the system on deck, we are required to consider accelerations as well from the physical movement of the vessel. So it's not only the operational elements of the hammer that provide us challenge, it's also the storing of the end system that provides us challenges with. You see the design considerations that we need to take on board for designing the sea fastening, so temporary storage of the system on deck. And that again is a challenge on its own. We talked about noise a little bit earlier, and while we do have aids and mechanical system designs considered to reduce the noise footprint of our system, we have as well operational aspects that we can incorporate in order to reduce the noise and overcome challenges with that. Noise usually increases for a known hammer with the increase of energy. If we can therefore reduce the energy, we can actually reduce the noise. However, if we reduce the energy, we may not drive as far as we would like to with a known pile in the known soil conditions. However, if we are increasing the blow counts, we can actually overcome a higher resistance. And that's what we call low energy, high frequency piling. We have designed the hammers that can actually vary the volume flow to the hammer and increase the blow counts quite significantly. The video on the right, and you will hear some sounds to that and see blow counts, shows you of what we're talking. The nominal standard blow count that the hammer runs at is between 30 to 36, and any blow that you see, of course, above 36 is therefore part of our high frequency, low energy piling. On the left chart, before I start the video, on the left chart, the dots are actually measured blow counts versus flow rate compilations that we have accomplished with our hammers, while the blue lines or the full solid lines are the model data. So it compares quite nicely with the model, but let's take a look at the video for now. particularly in the last one with the 75 blows per minute, you could see the hammer actually moving quite a bit. And it was not only moving down, but moving up again. And that's the flexibility or the elasticity that we have in the pile itself that actually pushes back onto the hammer. However, with 75 blows, if we take the graph on the left, the 75 blows, we can go all the way up to the green line here. That is 1,000 kilojoules. So 1/3 of the hammer capacity actually is available through this blow count. And that allows us to overcome resistances in the soil that we would get, could overcome nominal at a higher energy at regular blow counts. It reduces as well the noise on one side, but it reduces as well fatigue. However, the fatigue is a dependency on the number of blows at a certain stress level that you put on top of the pile. Therefore, it needs to be monitored and designed accordingly in terms of the pile sketch to anticipate. I'm getting closer to the end here, and we'll move over to drilling from my that Ivan will take on. But last but not least, I think it became clear that it is a massive undertaking that we are entertaining on a daily basis. Though only with the system itself, you could not do this. We are depending on quite a lot of engineering capacity and intelligence from engineers out in the market in order to overcome our daily challenges. For that, we are quite interested to actually cooperate and co-share our technology and knowledge to better understand the challenges from a different perspective. We are continuously working with our clients and partners in the market, sharing intelligence about our system design under NDAs in order to understand challenges like piling noise, like fatigue a lot better. In-house, we do perform drivabilities with and without our MNRU unit. We model underwater noise quite continuously and consistently, and understand therefore the need for improving or changing certain aspects of the piling grid. We can change this by the pile driving schedule, blow counts and energy levels, for example, or by incorporating an MNRU unit or secondary noise mitigation system. So while we are compared to a sledgehammer in the first instance, we've become much smarter about it, and we can accommodate a lot of different aspects and the challenges that we face today. With the increase in turbine sizes, we anticipate seeing further increases in our challenges to come, not only on the environmental side, but equally on the fabrication side for our tools. So we are looking forward introducing the 4400 hammer into the market, which actually happens right now in these days. The first 2 units are in the market and are driving first piles in March. And we're looking equally forward to the first large diameter anvil of 8 meters that will be introduced in later 2022 into the market. And thanks for giving me the opportunity to speak to you today, and I'll pass it back on to Ivan.
Thanks, Fabian. I just have to take control. Okay, so I'm going to talk now about drilling, and I'm going to start off with monopile drilling equipment, and then why we drill, and then some of the drilling methodology that's used. Okay, so I'm just going to move on. Yeah. Okay, just some technical difficulties with Zoom. So what we're talking about is a pile top drill. So the Action Group company LDD has significant experience in pile top drilling. Small piles when it comes to jacket pile diameter, but here what we're talking about is large diameter drilling, which is drilling of the monopile. So this is the LD 5000, which was a drill developed back for Gwinty Moore back in around 2012, 2013. The drill sits on top of the pile and it's hydraulically driven, which rotates the bottom whole assembly, and then the drill bit, which drills through the ground, and then the spoils come up through the middle of the drill pipes using an airlift system, right? So there's 4 main components to this drill. You've got a conductor or a pile gripper can, which sits on top of the pile. and which supports the structure above. Then you've got the power swivel, which rotates the drill pipe, power swivel here, and then you've got a mast and a carriage. So the carriage holds, provides the thrust down for the drill and also pulls the drill back up. And then you've got the drill pipe, which provides the movement, which transfers the movement from the power swivel to the bottom hole assembly on the drill, and also provides the conduit for the air supply down and the spoil to come back out. Okay, so the rotating drill head, that causes the drilling action. The center of the drill is about 5 to 5.1 meters, and then that can expand to 8.5 to 9 meters as it goes down along the monopile. The top of the monopile is typically narrower than the bottom of the monopile. So therefore the drill has to be able to get through that tighter neck. So we do that by holding back the underreamers till we passage through that narrowing. And then when we get down to the toe of the pile, we expand, or as we go down through to the toe of the pile, we expand and come out at the toe of the pile to drill. And as I said, an airlift is used to remove the spoil. So I'll just go through slightly that operation for you. Okay. So as I said, you've got the gripper can on top. So what happens is the carriage here, that's for the attaching and disconnecting of the drill pipe. So the drill pipe is what supports the bottom hole assembly. And as we're moving the drill pipe down as we're moving the bottom hole assembly down the monopile shaft, we install more drill pipe to make the connection, and then install the drill pipe, push down the head, more drill pipe, push down the head, more drill pipe, push down the head, right? And as I said, the air line runs down through the drill pipe, and that inserts air just above kind of a snorkel or a hole in the bottom of the drill, and then that creates air movement up, and that air movement up pulls out the spoil from around the bottom of the head of the drill and pulls it back out up through the top, and then that's discharged through the cuttings, discharged to the sea. The other thing is we constantly keep a water head in this system, so as water is coming out, we have the water pumps on to pump the water in. So if I just move on, so you can see here on the LD5000, the hole where the spoils come in, and as the spoils come in, as the air lifts up, it pulls the spoils in and then discharges it to the seabed or to the sea. Here we're just discharging overboard on a UK project. In some instances, we've been asked to manage the spoils, and depending on the different locations, those spoils can be maintained on a separate vessel and taken to onshore for dumping. But typically, the spoil is just the seabed, or is naturally occurring material that's not contaminated by anything, because we're just using air and water to make this thing work. So there shouldn't be any need for it to be managed from a contamination point of view. And then looking at the reasons why you would drill, there's two main instances in why you would drill. One is that you're installing a monopile and then you've got pile refusal. So as you're banging in the pile won't go any further, either due to skin friction, as in it just can't move given the friction that you're getting from the soil around it or from the seabed around it, or else you've encountered boulders. In each of those cases, with skin friction, what you would do is insert the drill and drill out the center of the pile, and then to target depth, and then take out the drill again, and then just continue, put back the hammer and drive on the pile to the target depth. If it's boulders, same thing again, take off the hammer, put down the drill, and then either, in some instances, what you'll do is if the boulder is in soft ground or soft soil, you'll end up just pushing the boulder down underneath the toe of the pile, and then you can advance the pile. Or else, if there's hard ground, what you end up doing is most likely obliterating or smashing the boulder against the hard ground, and then that causes the boulder not to be an issue anymore. The other instances is plan drilling, and this is where drilling is to be used as the main installation, as part of the main installation process. And we're seeing this happen a lot, or potentially happen a lot more on future sites. This being that, sorry, just this being that the soil conditions to be used, or the soil areas that developers are looking at, are more challenging, given that or in a lot of the established markets, the easier fields are gone. So we have to work with more challenging conditions. So first of all, looking at drive, drill, drive. Drive, drill, drive is where you start off with a hammer and you drive the pile to refusal, and then install the drill on down through the rock or whatever's causing the refusal. But you don't drill the complete diameter of the pile. What you do is drill almost the complete diameter of the pile and leave a lip or a shoulder around the edge of the socket for the pile to sit on. Then we extract the drill, put back on the hammer, and drive the pile through to the target penetration or target depth, which knocks the shoulder off, and that material comes into the center of the pile bore. Then the other ones are looking at socket drilling. So socket drilling is where you start off, you already know that there's hard rock there, you know there's no point in driving through it. So you take the drill, put it overboard, you drill a socket, you lift and install the pile into the socket, and then you grout the socket to the annulus. You grout the pile to the annulus. So that is putting cement between the rock and the pile to make sure that the pile is stuck to this, is getting fixature around the annulus or around the diameter of the pile, and potentially at the pile toe as well. Next one then is socket drilling, but in an instance where you have, so the first one showed just drilling a straight socket. In that we had no real overbearing or no material that would fall into the socket as it was drilled. So in some areas you're looking at, you've got an overburden material that could potentially fall into the socket that would fill up the socket or wouldn't allow you to drill through the socket. So in those instances, normally you drive a primary pile that could be hammered in with an impact hammer or could be vibroed in, get that down to where it's holding with the rock and there's containment, then install the drill, drill on through the socket, extract the drill, install the insert pile or the secondary pile, and then grout the secondary pile or the insert pile to the socket and to the primary pile that's already been installed. As I said, this is done where there's potentially material on top of where you're drilling the socket that could fall into the socket and not allow you hold the socket for enough period of time to install the monopile and grout it up as well. Moving on. So that brings us on to the question of grouting. So what is grouting and what's the applicability of it to monopile installation? So grouting from a simple point of view is mixing and pumping grout, or mixing and pumping grout into a structure. Grout itself is, in a lot of cases, when it comes to monopile grouting to sockets or grouting of piles in sockets, is typically normal cement. So your 42.5 or 52.5 standard cement that you get from any of the main cement suppliers, mixing that with water. Typically in an oil and gas installation, it would be seawater. Most likely in wind, there'll be a push for fresh water. And then the other option is using a pre-bagged blended material that's DNV approved to C502. So that would be from your big chemical companies like what was BSF, now Master Builders, the ITW or Sika or someone like that have got a material that has gone through the DNV certification process. Typically with a normal cement and seawater, or even fresh water, you get like 50, 60 MPa at 28 days. With a pre-blended material, you're looking at anywhere between 70, 80 and 100 and something MPa, 120 MPa after 30 days. Just talking about the equipment that we use for grouting. So the grouting equipment that we use and also the drilling equipment that we use is all modular equipment. So all of it can be put on the back of the truck and brought to a site relatively quickly. So the LDD drills come straight out of Cornwall on the back of the truck to whatever site they need to get to. And the same with this grouting equipment from Core. All of it can go on the back of the truck and be brought to wherever it needs to go. So here you've got 50-ton silos. You can put 2 of them on the back of the truck. The silos hold the bulk cement. And then you've got a grouting unit here, and you can't see a 20-foot container workshop that goes with it. This is the grouting unit when it's set up on a deck. Here it's set up in the yard in Crookstown. So the operation is basically, these silos are loaded with cement. That cement is blown by air into this hopper on top of the grouting unit, and then that cement gets dropped into a high flow of water, a jet, and then a jet causes turbulence, and that mixes the grout or mixes the cement and water together. And based on analyzing or managing the density, monitoring the density of that water cement mix, we can manage the quality of the grout that gets sent down the line by these grout pumps here. So all of this is a contained system. It's a modular system, a contained system. There's no dust or cement particles getting out to the atmosphere. And then it gets pumped down 2-inch lines or 3-inch lines, depending on the material. And those lines go into the structure or into the stinger that installs the grout into the structure. So typically, these are typical ways grout is normally used. So here is a monopile where the monopile has been installed, and then we're dropping a transition piece onto the monopile. And in that instance, we're going to fill the annulus gap between the monopile and the transition piece of grout. This is from the Rampion project, which was about 30-40 meters cubed of grout per structure. The next one then is, this is a jacket that's going to be installed, and the piles are driven through the jacket sleeves and then grouted. Then the piles are grouted to the jacket. That grout holds the jacket to the pile and transfers the force between the two. And then the structure on the right-hand side is a clamp that was installed on a Norwegian project. This was about 100 meters cubed of grout that was installed into this, so about 200 tons. You can see the size of the diver versus the size of the clamp. In that instance, we installed grout at the bottom, and the grout circulated around and came out the top, and it was a straightforward operation. Moving on. So as I said, typically, if it was a socket, a grouted pile installed in a socket, and we weren't drilling through the pile, we would potentially use grout lines. So there would be pre-installed tubular, pre-installed grout lines going down to the bottom of the monopile, and our grout lines would connect to that at the top, and then the grout would be pumped down to the bottom, and then we get an overflow here where the grout meets the seabed. In a job where you've got an insert pile, and it's more challenging to manage grout lines going down to the bottom to the insert pile. So what we typically use is stinger. So I've drawn in the stinger here in yellow. What is a stinger? Stinger is typically a 2-inch line or 2-inch pipe that can reach all the way down to the bottom of the hole that we've drilled that we need to grout to. Here's an example of some that we've used on a jacket project. Typically on a jacket project where there's grout lines, they've used as a backup. On an insert pile like this, we probably use it as a primary because it's an easier way of doing things. And these are some other examples of stingers that we've used to grout up smaller bore piles. So when we're looking at a typical grout installation, you're talking about 20 to 30, maybe 40 meters cubed of material to be pumped. The system here on the left-hand side is what we've recently used on an offshore installation in the north. So we've got our 20-foot containers here with normal cement in them, and then we've got our grouting unit. This unit here does 20 meters cubed an hour of grout. Which is fine for a jacket installation, because you're talking maybe 15 meters cubed per pile sleeve on a typical substation installation in offshore wind. The unit that's on the right-hand side does 100 meters cubed an hour. This unit is one that we've developed for monopile grouting installations, where we need to pump a large amount of material as quickly as possible into a monopile structure. As I said, each of these units here do 50 meters cubed an hour of material, so the two together do 100 meters cubed. You've got, I think, about 120 tons of storage per silo here. This will be installed on the back deck of the installation vessel, and then we start We charge these up. These are auger fed, but they would be pneumatically fed with material from the other silos on deck, and then we auger the material out into the pan mixing units down here, and then the concrete pumps below. So this is just to give an idea of the potential. There's a potential change coming in the market where there's going to be larger, more challenging projects that require larger hammers like the 4400, larger drills like the LD 5000 and the next generations of drills that we're looking at after that, and larger grouting equipment like this type of unit that we've built. Fabian spoke about supply chain. In core grouting, we've built the vast majority of the equipment in Ireland, and I think we've used a lot of the Irish supply chain to support the development of that equipment as well. The drills, a lot of that has been built in the UK, and then the hammers themselves are built globally due to the need for very specialist foundries, I suppose, to get a lot of the key components. And then moving on to some of the other considerations for the future. As I said, I think the projects are becoming more technically challenging, and that's due, I think a lot of easy sites are gone potentially. Also, people are becoming more aware or familiar with the risks of using more challenging ground conditions, and are probably getting more adept at managing those risks. The other thing I see is there's going to be a high demand for people for these projects. That's both onshore and offshore, engineering across the engineering disciplines and the technical disciplines, which is an opportunity for, I suppose, a lot of the people on this call. And then there's a big demand for equipment as well, which means for investment across the supply chain. I'll move on to, I think that's our last slide. And then, so from there's one thing I'd like to say, from a GDPR point of view, we can't get anyone's contact details. These are mine and Fabian's contact details. So if you want to contact us about any of the details, or any other questions out of regard the services that we offer, just drop us a note. We're always interested in talking about wind farm and wind farm installation and the like. Okay, thank you.
That's fantastic, guys. Ivan, you might copy those email addresses into the chat function as well.
Yeah,
maybe
yeah,
it might be helpful. So guys, thank you very much. Very interesting lecture. Lots of engagement. There's over 150 people on the call this evening, and I see already there's the bones of 30 questions have already come in. So it's a great indication of people being really engaged with the topic. And I think possibly you've also hit the nail on the head there, Ivan, that people see that there's an opportunity there for I suppose Irish engineers and Irish companies to get involved in what will be a huge market going forward. So folks, there is a Q&A button down at the bottom of your screen. So if you would like to ask questions, by all means, fire them in there. So I suppose Ivan and Fabian, I might as well kick off with the questions. As I said, there's quite a few of them. I suppose the first few questions came in there when Fabian was talking about noise mitigation. I suspect some of these questions might have been answered in the meantime, but look, we'll go through them anyway. So the first question: how far away from the point of impact can the 4,400 kilojoule hammer be felt? I suppose you've spoken about Fabian, about the limits that are allowable, but is there any indication of how far away somebody would actually notice that the unit is being used?
Yes, very interesting question, as a matter of fact. Maybe I can answer this in conjunction with experiences that I made myself when being exposed the first times with pile driving. When I joined the company Mink, we tested a piling hammer in the background, in the backyard of our premises here. We have a test pad that sits about 200 meters away from the office, and we are in an industrial area located with lots of storage and warehouses around it. The impact from a 500 kilojoule hammer I could feel in the office. I was sitting on the second floor of the building, and my screen was actually shaking. At the same time, we had claims coming in from the next village over, where individuals could feel the impact, of course, through the soil formation. And the next village over is across an autobahn and about 2 kilometers further distance. So you physically can hear it, of course, through the airborne noise by impact. Steel to steel impact is quite loud, but you can also detect it by ground vibrations. I would not claim that anybody in the village could actually feel the ground vibrations, but we certainly could about 200 meters away. So as you can imagine, that it's a lot of energy going into the ground and through the pile into the ground, and it can be felt at a distance. In terms of recognizing or hearing, feeling this in the marine environment. A couple of years back, we got a video from our underwater noise recording, actually from our piling hammer, and we could hear a secondary sound in the background. So you could hear always a blow from our hammer, and then seconds or milliseconds after that, there was a second blow in the background, and we couldn't really make any sense out of this. And that came actually from our competitor, who was piling about 40 kilometers away. So the medium that you actually consider in this environment, so be it air, be it water, or be it the soil itself, transfers, of course, sound and energy quite differently, as we know from earthquakes equally, and it travels quite far distance. Yeah, so the environmental protection measures that we put in place by means of primary or secondary system are becoming much more critical and much more important, of course, as we have learned through these elements. So we can pile today in residential areas. We have noise protection aids for that. Nonetheless, you still will hear the piling noise. Equally, we do have the underwater protection measures available through our system technology or through secondary systems in the market. But you can recognize it, and when you hear it, you know it.
Yeah, very good. Yeah, I suppose just my own point of view, I'm involved in, I suppose, what would be called heavy civils landside, but the scale, I think, puts us to shame. Certainly the size of the units being involved are just absolutely huge. Two kind of similar questions there, which were kind of asked fairly early on, so I suspect you've kind of answered them, but I'll ask again. Just wondering what stage the NMRU unit is at, and whether it's actually been, used on an actual development, live development.
It's fully commercialized, so we are using commercial systems in the market today. We're driving piles right now, actually, with multiple hammers with the NMRU.
Brilliant. Another one that I've seen a couple of versions of during the presentation, and I think it was asked as well about drilling, but this particular question is about during pile driving, the horizontal and vertical stability and how it's adjusted, especially considering the fact that you're in a marine environment, and you have to deal with swell and that. Is it all down to kind of computer control systems, or is there a kind of a more old-fashioned approach to it?
Is that for drilling or driving?
Well, take driving.
Driving. Well, the pile itself is usually held in place. So the reason why we put a sledgehammer on top, because the sledgehammer actually resembles the pure mechanics behind it. If you imagine you drive a nail into the wood, you have two fingers that hold the nail in your hand, and you drive with the hammer on top. So we provide the hammer, and the two fingers are actually pile gripper system that are mounted to the side of the vessel. That ensures only the relative position of the pile and certainly avoids it from all tipping over. But it actually avoids as well to get to that place where it becomes more dynamical in terms of a tip over. There are mechanical aids in place that hold the pile in a vertical position.
Good. Somebody asked, are there any disadvantages to using the NMR unit? Does it have any adverse effects, or loss of efficiency, or Well, what we do is
the pile driving hammer originally was developed, the MHU particularly, but oil and gas pile driving hammers as a whole particularly were developed to provide the highest efficiency possible. And efficiency, of course, is not necessarily defined by the cost that we have for our system, but the entire asset spread that is associated for undertaking those kind of installations is quite expensive. If we are going into deep water, the vessel costs quite quickly in the range of $500,000 to $1 million a day, depending on the type of vessel that we operate from. So our costs are quite minimal, and appreciative of that. The quicker we can drive a pile, the more efficient it becomes. Though the efficiency that we have put into the design at the time translates today into environmental concerns, let me call it. And for that, we try to smoothen the impact a little bit and extend the force over time. With that, of course, you have to cope with a couple losses. Physically, our hammers are designed to actually be oversized for the undertaking, and an oversized system means we don't have to drive at maximum energy. That as well means that we are actually putting less noise onto the hammer rather than a perfectly 100% capacity design system. We are providing 120, 150% capacity design system for the piling needs that we have, and we can drive at a lower impact speed and therefore have a lower noise. With the MNRU, then, of course, there's an impact coming from that, and the extending the force time diagram or a little bit further out, of course, reduces the pile peak, which is fatigue friendly, so it's a cost saving on the design of the pile on one side. However, there's an efficiency loss associated with that as well. Yeah, it is estimated in the range of 5 to 7% only. So we can quite easily and nicely accommodate that.
Sorry, just move on again because there's plenty of questions. And apologies, Ivan, I'm doing these in sequence, so your turn will certainly come.
I get a cup of tea.
Absolutely. You had referenced that the effect in the oil flow was very high, something over 4,000 liters per minute. Are there fail safes in terms of in the environment, and that are there fail safe systems in place in the case of a rupture or similar?
Firstly, we certainly use not an ordinary hydraulic line for that. So it's a multi-protected hydraulic line that is quite armored overall, and we have high standards in order, and even if we have a slight scratch on the outside of a hydraulic line, we would exchange it. So the expectation of the integrity of the system is quite high. Second, yes, if you have a rupture of that unexpected rupture, then you would have a spill, and for that reason, we use environmentally degradable oils and fluids only. That is not doing the trick overall. You still would have a spill and you would still have something in the environment, but that's on the forefront of us and the foremost attention for us to have this actually avoided. Yeah. Yes, the risk is there, but the standard that we actually put out in order when we operate the system is at a level that avoids or mitigates most of those risks. It doesn't avoid it at all.
So basically a large margin of error, that's good. To do a couple of questions in relation to how the kind of traditional piling, hammer-driven piling compares to things like vibro hammer or suction pile installation. Are they? I don't know. Are they technologies that are used for this type of application?
In offshore wind, there are vibro installed piles equally as there's a suction bucket design. All of these have their right to be there, in my opinion. And by trade, I'm a technical engineer. So I used to design suction piles myself for oil and gas assets in the past. However, none of these other systems is a proven system in terms of you put an energy in order to penetrate and you understand what load bearing capacity it has. So that's the benefit that you get with a driven pile. As well, the area or the width of soil conditions that you can install a driven pile is significantly larger and provides much more contingency in terms of unexpected soil conditions And you can only be as smart as your soil report is when you actually go out and install some piles. So yeah, all of these systems are in the market. They are continuously being used. We do see now systems where a rock socket is being drilled actually and filled for a large monopile is filled with sand, and subsequently a monopile is vibrated into that rock socket with sand. That doesn't avoid us or need us for that installation, and it's a viable system technology as well. We are keen to provide a reliable foundation in the first place. We are not shy, even from a hammer perspective, to consult clients towards, listen, you may be better off with a different system. But the width of foundation applicability that we have with a driven pile, or even a joint collaboration between a drive drill, drive pile. So drive a pile until it hits refusal, then clean it out with a drilling system in order to reduce the soil friction, and then finish it off driving. So the width of soil conditions that we can accommodate with that is quite significant.
Yeah,
and that's the ability that we can provide through Mink or even collaboration and resistor opcodes.
So there's that's one of the major advantages, the versatility of the system.
I think just the market's expanding a lot, and there's room there. People are looking at different options on how they get their foundations in. I think there probably will be more vibro projects. There will be more suction bucket projects. There will be more drilled projects and more hammered projects. It's just, there's such growth there, but it's always ground dependent and project dependent what the client will go for. So, yeah.
That's fair enough. I see some drilling questions coming up there. One last one for Fabian. They're from Joseph Barry. In general, do Mink hold the risk for hammer ops? And he also asked whether the hammers are considered off-shelf items, or are they designed for specifically for each project?
If we would design the hammer for specific projects, we actually wouldn't be able to do any projects. The lead time for some of the components is in excess of 12 to 18 months to procure this, and then of course the design phase on top of that is jeopardizing, for example, a new size hammer. Our hammers are modular designed, so the smallest hammer has quite similar components than the largest, but it's of course different dimensions, different sizes, different weights. We do learn through the process of upscaling or downscaling. The smallest one is actually a downscaled system from our first hammer that we had, while the largest one is an upscaled system from the first one we had. And through this process, it is a modular system that has a versatility and adaptability to different pile diameters, water depths that can meet a lot of challenges. The longest pile we've driven to date is 270 meters long at 96 inches diameter. So that's close to 2.5 meters diameter. We've driven piles just a couple of years ago that were 4 meters and needed in excess of 20 to 25,000 blows per pile. So there's a lot of wear and tear. And not monopile is driven between 2,000 to 5,000 blows per pile, depending on soil conditions, of course. So the modularity actually allows us to reduce costs for the installation. Nonetheless, those systems are costly in the procurement and setup and in the entertainment as well. But a bespoke system for one project, that would not be economical. And I'm sure we would see much more vibro-driven piles and suction bucket pile foundations than a driven pile in that sense, if that would be the case.
I suppose just kind of switching over to the drilling, Ivan, first one up there, I suppose in terms of drilling rock with the LDD, what kind of strengths of rock can be drilled through, and what are the kind of maximum depths that are available?
Okay, so can we drill through rock? Yes, we can drill through rock. Up to about 100 MPa is where we're drilling at the moment. So we're completing a project in China where we're drilling 100 MPa using the LD 5000. Then when it comes to what's the maximum depth, that's a challenging question to answer depending on what you're trying to drill into that. So typically on a monopile project where we're looking at drilling it in challenging conditions like hard rock, you're talking about 20 meters. So you're talking an 8-meter diameter hole in hard rock, 20 meters deep. So that's what we're looking like at the moment for 8 to 9 meter diameter piles, right? When it comes to, we have drilled projects in the past, particularly for jacket pile installation, where we drilled a lot deeper than that, but like 40, 50 meters depth in not as challenging ground, not as hard rock though. So with anything with drilling, it's always project specific, because like the equipment might be standard, but the methodology and the drilling rates is really dependent on any given soil conditions within the site. Okay.
Yeah. Sorry, no, I'm just going through the kind of couple of repeats there. Somebody, and I kind of had that question myself. They're wondering, you mentioned the airlift system for bringing spoil back out, and they're just wondering how that actually works.
So what we have is we've got air compressors on the deck of the vessel, and the air compressors provide a lot of compressed air through an air hose or an air line down to the bottom of the drill, and then we insert that. So you've got a hole. Sorry, you can see the screen. You got a hole here at the bottom of the drill, and underneath the hole at the bottom of the drill is the face that we're drilling against, and all the bits of material that have been broken off. So we insert the air here above. There's the drill pipe goes up here. We insert the air, and then the air rises up. Bubbles up through the water column. So it's a complete water column. The air bubbles up through the water column, and that pulls the rest of the water from around the drill head up. So we're constantly putting water into. We constantly have a head of water pressing down on the drill, right? So the pile itself is full of water. It's flooded. We're constantly putting water in, and then we're injecting air near the bottom of the drill head, and that causes, as the air rises, it causes a suction effect that kind of hoovers up vacuums up the spoil around the wellhead, the drill head, and then that shoots up and takes all the water, shoots up with the air and takes all the spoil with it overboard. And then we're constantly injecting more water. We're constantly flooding, keeping the pile flooded with water and keeping the airflow going. They've asked what's the amount of air. I'd have to check. I just normally count the compressors that are on, but I'd have to check what the standard cubic, or the cubic feet per minute that we're using. I can't quote that at the moment.
Just one there about the grouting. Like you had referenced normal cement, and they ask if it cures underwater, and thought that special mix. And if I could just add to that, you had also referenced that in oil and gas traditionally just normal seawater been used, but that in wind turbines they're looking for fresh water, and I was just wondering why.
So just to answer them, so cement does cure underwater. It's happy to cure underwater. Like cement it's a chemical reaction. So cement reacts with water, and then it doesn't dry, it cures, and it's happy. It cures very well underwater. So that's the first thing. The second thing is, typically in oil and gas, we've used seawater. Why have we used seawater? Because there's loads of it available. You just take it off the firewater mains and react it with the cement. Typically, it's underwater as well. When it's a jacket pile, it's normally subsea, so people aren't worried about chlorides. Aren't worried about the chlorides interacting with the steel. In wind, it can be a little bit more questioning regarding that, even though it shouldn't be a problem, or it isn't a problem. Like we've proven it in oil and gas, but there's more questions. Typically in wind, if DNV or anyone are certifying, the structure, DNV don't like to see normal cement used on a project. So I'm just speaking from experience. So I've heard DNV don't like to see normal cement used on a project. Normal cement isn't certified to C502, the DNV standard. So DNV normally look for a pre-blended material. The pre-blended materials only work, or they will work with seawater, but they are, in order to stay within the guidelines of the manufacturer, you have to use fresh water. And why we don't like using fresh water, the installer doesn't like using fresh water, is you have to take freshwater tanks offshore with you, or you put an undue burden on the vessel freshwater system or drinking water system, which can be a real pain for vessel operations. So, does that explain?
Yes, that's fair enough. Those are Barry there asked for LDD. Is there much downtime expected on an average project, if such a thing exists?
Yeah.
And I suppose who bears the risk?
So who bears the risk is who you said in the contract bears the risk. So that's at contract stage. And then is there a lot of downtime? It depends. Like, it's like any project. Offshore and onshore projects are the same. Like, everyone suffers from downtimes on projects. Yeah. But one thing that you would do as part of your planning at the start with the operations team on the contractor side or the client side is work out where the risk of downtime is, and then how do you mitigate that from like a spares philosophy or crewing philosophy or whatever, so that we can manage the downtime to the least amount potentially. Okay.
Yeah. I suppose somewhat of a lead on from that. Somebody asked what would be the lead in time expected to mobilize a drill.
So we've done it. So I see the question as well, and it's like, when people look at projects, they look at drivabilities, and as part of doing the drivability, you make a risk assessment on whether we do we need a pile drill, do we need a drill for pile refusal, and that's down to their contracting strategy. Do we need a drill for, is pile refusal that likely, and then do we need a drill to cover it? If someone rang us up in the morning and said, can we have a drill to drill 8 meters? You can't tell them, like, we don't have one sitting around all the time. So, you know, most likely you wouldn't have a drill available when people ring you up like that. But if they did, if we did have a drill on standby, you'd get it to someone within a week, I'd say, a week or two, depending on the time of the year. Typically, though, what is looked at is a contractor, if they thought pile refusal was a potential, they would have a drill on standby, either on the vessel or on the quay side. Plus, what I've seen at the moment is developers are looking at any way they can to mitigate the risk of using, to mitigate these risks. One of the things that they're looking at is boulder surveys, doing boulder surveys and then altering the location of the monopiles to try and avoid the boulders. And that would potentially minimize, you know, weird pile refusals due to boulder. But then if it's skin friction, or if it's pile refusal due to actual hard ground conditions, that should have been identified at the start of the project, I would say. Anyway.
Yeah, that's fair enough. I might integrate 2 questions there. I suppose they're wondering in either scenario whether the vessels are kind of directly chartered by yourselves, or whether they're kind of in with the contractor. And I suppose just because it's across both of you, installing a monopile, you know, like, what's the typical timeline for a hammer versus drilling?
Okay, so just on the, typically we provide services to the back of other people's vessels. So the vessel is chartered by our client. We have in the past, particularly on nearshore projects, LDD have managed vessel, have taken on the vessel scope and managed that for the client. And then we do have an integrated service offering within Action, where we look at managing the vessel and all the other services. But on a typical or challenging monopile installation, I would see us just providing the services to someone else's vessel. Then when it comes to, I'll let Fabian answer what's the typical time for installing a monopile from a hammer point of view, and then I can say drills.
Well, typical time for a driven monopile depends on certainly the soil conditions and what we can put on the pile. The pile is usually not designed critical for the fatigue that we use, so energy is not a massive limitation factor. Most piles that we drive are driven with 2,500 to 3,000 blows per minute, and that takes us approximately 100 minutes to drive them. Yeah, the rotation though on a monopile per month. So if we are looking at a wind farm installation and then see, of course, the additional time required to pick up the next. This is not on Mink, but pick up the next pile, put it into the pile gripper system, and then put the hammer off that pile again. The rotation from one pile to the next ranges somewhere between 1.5 to 4 days, depending on how the methodology is set up and how the contractor actually feeds the piles for the installation. Yeah.
So you're saying between 1.5 to 4 days for a big pile installation, for a
big piles from one pile to the next. The physical driving is somewhere in the range of 1 to 2 hours maximum.
Yeah. So when it comes to drilling, then it's all dependent on the soil conditions, right? So if it's a drive scenario and you've driven to penetration and then you are driven to a certain depth and then you need to switch out to put the drill on top instead of the hammer, you're talking about potentially 12 hours to get the drill on top, to get the hammer off, get the drill on and run the drill to depth. Then you drill out, you're talking with up to 100 MPa, between 60 and 100 MPa, you're talking about 0.3 of a meter per hour of drilling depth, up to 0.3. Then at up to 60 MPa hard rock, you're talking about like about 0.5 meters per hour in depth that you can drill. And then in like gravelly clay soils or ground conditions, you're talking potentially 1 meter per hour of depth that you can get. Then when you've drilled that, you take off the drill and put back on the hammer to do the drive, you're talking another 12, up to 12 hours depending. And then you hammer to depth again. So I would say if you're including drive, you have to add a day to a standard installation. Then we're looking at projects now where they're just starting that drilling straight off the starting drilling. So you're probably talking a day or two that needs to be added to each pile installation. So you're probably talking, Fabian's saying 1.5 to 4 days for a big monopile. You're probably talking 3 to 5 days for a drill pile installation. That's including the grouting as well. If you've got a decent sized grout machine on there, that's going to do, 50 to 100 meters cubed an hour, something like that. So you're probably talking like five days for a monopile installation.
Okay. So next question there. With more projects using an extended monopile rather than no separate TP, the driving will be directly on the flange that interfaces with the WTG tower. What mitigations are in place to ensure the foundation/tower interface flange is not damaged?
The primary mitigation that we use is, of course, early engagement with the designers and the owner of the pile. So the design and a sound design between the anvil that we provide and the flange that we drive on is required in order to mitigate that. There are aspects that need to be considered in terms of the energy, the design of the flange itself. Is it a flat one or is it actually with a slightly tapered shoulder system that allows us to mitigate any damage subsequently? We understand the challenge and equally we communicate the challenge early on, as early as possible. So that means 2, 3, 4 years in advance to the actual installation with designers across the market, even if we don't know what designers design the monopile or the flange itself. But it's the transparency that we put in order to mitigate and educate people from our side with the needs that our system brings across to the designer that we are not directly involved in. That's the primary measure of mitigation. Other than that, of course, we do monitor the performance of the system and we do take the design of the flange and model this before we actually go out and ensure that we don't have too much movement on top of the flange that would damage the flange subsequently. That could mean it limits the hammer in energy, and that is a part of the discussion that we have then with the contractor and the owner for the wind farm.
That actually, I think, answers part of the next question, but question, can you give any information on the type of integrity and load testing, pile testing of these monopiles? I suppose once they're in place, how, what's the testing procedure for them?
Well, physically, there's from civil side there are pile load tests being performed on the real life system subsequently to the installation. You don't see that in offshore wind necessarily for a monopile. You do see the pile monitoring systems, GRL-WEEP or all-NAMIC systems that are being put on the pile side in order to monitor the installation itself. That, of course, ensures integrity of the foundation pile on one side, and through hindcast analysis using CapRep programs, again, you can then model the capacity of the pile quite reliably. That are the common measures though notably those piles are over-designed for the purpose, quite over-designed for the purpose, and there's a lot of contingency put on the design in terms of its length, actual capacity, but lateral load-bearing capacity and flex through the system as well. And that provides the contingency. The biggest challenge is really ensuring installability rather than the loadability. And if that can be guaranteed, then the system is
more than adequate.
Just looking at, you've got a question there about 12 meter and 12 meter monopiles. Is the installation supply chain there to cope with that? So just looking at that question, we're currently developing, our current range of drills go up to about 9 meter diameter. We're currently developing a drill that will be able to drill at 12 meter bottom diameter. So it will go from 8 down to 12 as it goes through the monopile, right? So that's the first thing. Is I'll let Fabian talk about the hammers that he's developing, but the other part of the supply chain is the installers, right? So in 2009, I think there was 6 vessels that had a crane capacity of greater than 2,000 tons that could install offshore monopile foundations, right?
Yeah.
It looks like by 2023, 2024, there will be between 13 and 16 vessels on the international market that will have the capacity for installing monopiles of greater than 2,000 tons. So people are seeing this within the supply chain, and they're investing in the equipment to install this, to install these projects. We're investing to make sure that we're able to install these projects. The next thing is, will the rest of the supply chain follow through, and will we have the people for it? Because it looks like there'll be a bottleneck at some stage. Will everything be available for it? But I'll let Fabian say about the hammers, because that's another subject that we're looking at.
Well, physically, the monopiles, of course, grow in size and capacity to physically build a monopile with a plate thickness of, or wall thickness of 150 mil, 15 centimeters. That capacity is available today, actually up to a diameter of 14 meters. We don't anticipate that the diameter on top of the pile will grow to that dimension. We see 8 meters quite reliably and consistently. We don't see much above 8 meters at this time at all. It's really a design consideration and design discussion that we have with those designers as well. What is the reason for that? And educate these persons and companies as well in terms of what our challenges are from the supply chain. To this day, there's no forging company able to provide a plate, anvil plate, larger than 8 meters. So that's the maximum, actually. And after that, we actually, we fly to Mars rather than build a plate larger. Or somebody needs to cough up quite a couple million of euros or dollars to actually build up this capacity in the supply chain. And this is not Mink, this is outside of Mink. Yeah. I would not anticipate that we see top diameters above 8 meters in the next 5 years. But anything is possible after that. And the question is, how big are turbines actually becoming? And that's a big uncertainty to this day.
I suppose it's a separate issue, but is there any, how should I put it, efficiency in the actual turbine design that would see, the same size monopiles and the same, tower going on top of it, but a more efficient actual generation system that would see, increase generation without an actual necessarily a physical increase in the towers?
Anything we do is coming actually from the top rather than managed by us, meaning the wind turbine generator, actually the load that needs to be burdened onto the foundation elements. Equally, the wind forces and environmental forces, sea states, and need to be, of course, carried by the foundation pile itself as well. Through the wind turbine developments over the years, and we're talking 2 decades plus at the time, the first generators that came out were gearbox-driven systems. So they had a massive, large gearbox that provided a lot of weight on top of that, on top of the wind turbine generator itself. With the direct drive turbine development, that rate could significantly be reduced. So even a 10 megawatt turbine is lighter than a significantly gearbox type 5 megawatt turbine a couple of years back. This is technology advancement and developments that we see on multiple fronts. We do see this within Mink, we see this in LDD, but we see this, of course, in the entire market. So be it in size, increasing in sizes of vessels that are being put out for installations, be it for the applicability of a monopile in water depth. So I saw a question there for water depth and monopile applicability as well somewhere. A couple of years back, we anticipated monopile being usable in water depth up to maximum 30 meters. Today, we're driving monopiles in 50 meters. And that's the extension of technology and capacity that we all contribute towards that allows us to provide a more economical system for the installation at the end.
Just conscious of time, you have two questions left, Ronan. The first question with regards to percentage of the market that's looking at this drilling methodology. I would have said 3 or 4 years ago, people kept away from this. You know, developers didn't look at this as an example. Like drilling and grouting large monopiles was something people shied away from. Recent projects, people are gaining more experience with this. So I see potentially 1 or 2 projects per annum from 2024, 2025 onwards that will use this type of technology. And the areas that it'll most likely be is like France, potentially Ireland, potentially Poland, and most likely Japan as well, due to the limited ground areas, the limited seabed area that's available, and then the challenging conditions in those limited seabed areas. So that's what it looks like. So it looks like there's this is a market for the future. And as we develop the technology more, I think people will be more confident about using it, something like that. Okay. And then the other thing is we are was just a question there. We are building new drills, new pile top drills that are bigger and new subsea drills that are bigger. So the next advance we will do to support these type of projects is instead of putting the drill on top of the pile, we'll just stick the drill on the seabed and drill the socket directly from the seabed. That allows us to do it from the larger floating vessels as well, and allows us have a more efficient operation. We've currently got designs and are working through bringing that material, that capability to market. So over the next few months, you'll probably see more about that. Yeah. Sorry.
No, perfect. Look, it's a great indication of the interest, the amount of questions that have come through. So look, I think maybe look, I might draw it to a close there.
Ronan, if I may take the last question that's still left.
Like
quite interesting one. Apologies.
You like that?
Quite interesting one. You know, the minimum. There's a question posted. What's the minimum energy that the hammer can put out during a soft start? So it must be somebody, although anonymous. It must be somebody with a backbone on piling. It is big, of course, to have a start on the pile driving, and particularly if we have those large systems. There's a lot of risk associated with that. So if you just go out, start the hammer at full energy, you're actually entering into something that can be quite adversive to the entire infrastructure that you put out and people inside. The Mink hammers can be dialed in at a minimum of 3% of nominal energy. So a 3,500 kilojoule hammer can drive as little as at 100 kilojoule actually for soft start. And that gives us a continuous bandwidth of 3% to maximum 100% that we can run this hammer at single blow modes or continuous blow modes. And that is one of the massive risk mitigation measures that we actually provide with the system technology today. And that development as well is a development that we have extended from where we were prior with the renewable energy market and the demands and challenges that we've experienced over time with that.
Brilliant. Thank you very much. Guys, fantastic lecture, very, very interesting. I suppose just a lot of people, I think, on the call who are possibly involved in the industry at some level. A lot of people, I suspect, that are maybe perhaps interested in getting into the industry, seeing it as a possible future career, and people like myself who just have a general interest in engineering and are just awed by the scope and the scale of the work that you're doing. The virtual platform has, great advantages. For example, Fabian can join us from Germany. Unfortunately, it does mean that we can't do the traditional round of applause that we'd normally get in an in-room lecture. But as I said, we had at one point over 160 people online. We had 30 or 40 questions, so absolutely great engagement there, and I think an indication of the interest and the quality of the lecture. So on behalf of myself and on behalf of all the attendees, I'd just like to give you my sincere thanks, and perhaps at some point in the future we might have you back again to give us an update on new developments. So thank you both again, Fabian and Ivan.
Pleasure.